Permaculture provides us with tools to make decisions that are mindful of all life. Seriously, they help us create a better world for ourselves and the generations that will follow us, all while caring for the birds and the bees and the flowers and the trees. If you've read a great book on permaculture or studied it for a while, then you know how to design a life that minimizes waste and is mindful of how you use resources. You're already refusing, reducing, reusing, repairing, and recycling, and so much more. But what forms does permaculture take when we move beyond the garden, backyard, or farm field and explore other human systems? What does design look like when we consider something larger than the scale of our household or neighborhood? How are cities making decisions like the ones permaculture practitioners make every day to reclaim nutrients, reduce energy use, and produce as little waste as possible? To find out, I spent a day in Washington, D.C. at the Blue Plains Advanced Wastewater Treatment Plant talking to Chris Peot, Director of Resource Recovery for DC Water, and April Thompson, Senior Director of Bloom, about how DC Water and its nonprofit arm, Blue Dot, are processing all of the municipal water for the capital of the United States, a city home to more than 700,000 residents, into a safe and effective fertilizer, potting soil, and other materials for use around the home, farm, and garden, and deepening their commitment to environmental protection by keeping hundreds of thousands of tons of waste out of our waterways and landfills. As they're the experts on this, let's have Chris and April tell us more.
Bloom came about when we've for many years had a long and successful biosolids recycling program. We made a lime stabilized Class B biosolids by EPA standards, and we gave it to farmers. This was before we had digesters. We made 11 or 1,200 tons a day. It was 70 trucks a day that came out of here. But we weren't extracting any value from that. We were paying somebody to take it away and give it away free to the farmers. And then the farmers would come to permit hearings and say, oh, the reason I'm doing this is because it's worth $300 an acre to us because of the fertilizer and the carbon and all these different things. So we decided that we wanted to have an environmentally sustainable biosolids program that could return carbon back to the soil, make a product that we could sell to the public, and create clean, green, renewable energy. So we designed digesters with the idea, every piece of equipment that we chose with product quality in mind. We wanted to make sure that it was going to be a low odor, very stable product that we could sell to the public. And we settled on thermal hydrolysis, which is high heat, high pressure, followed by digestion, which would give us a Class A biosolids product by EPA standards, which means that it's completely pathogen free. We can sell it to the public. And when we developed this product, we saw how beautiful it was, and it really is a beautiful biosolids product, and we decided we wanted to brand it and sell it, and we branded it as Bloom. Got a beautiful logo, we have a website, bloomsoil.com. And then we hired Blue Drop to help us with the marketing, because I have a staff of engineers who are very bad at marketing. So we hired April, and she is the director of marketing. We have a couple salespeople. Blue Drop is a nonprofit arm of DC Water. It is an arm that is designed to help us generate non-ratepayer revenue. So most of our revenue comes from ratepayers, people who pay their water bills. And we have a lot of assets and a lot of opportunities and a lot of ways that we can generate income, either through intellectual property, patents, consulting, because we have knowledge. And Bloom falls under that too. So this is non-ratepayer revenue that's coming in because we are now selling some of our biosolids product. So it was a perfect match for us to hire Bloom to do the marketing for this. So it's a nonprofit arm of DC Water that has non-DC Water employees employed, like April. I'm never sure if I get that completely right.
Yeah,
it's close.
Yeah, it's a nonprofit LLC. I guess
Okay.
that's the only small distinction,
Right.
Okay. So how does that relationship work then as you are selling these biosolids to the public as Bloom? How does that work within this umbrella that you exist in?
So as a nonprofit LLC, the Bloom's the limit, which is 450 tons a day. That's how much we have to sell. And this season, we're on track to sell out for the next few months, or have been actually.
And that's 450 tons a day, every day, year-round, through the systems that you've developed?
That's correct.
And what's the application rate then for your end users, like tons per acre? Is there any information on that exists so far?
Sure. It depends on the end user of the product. If we have a farmer, we have to make sure that they incorporate it into their nutrient management plan. So it all depends on what they're growing. If it's corn, it's a higher application rate than something else. Anywhere between 10 and 20 tons per acre for farming. And we have people who use it for restoration. There's different application rates for that. Landscaping is completely different. So it's prescribed differently for the different end users.
We also have different products. So what we call fresh bloom, which is the bloom fresh off the belt, is our farm agricultural product. Also have a product called cured bloom, that's essentially the fresh bloom air dried to a consistency of potting soil that's bagged and sold in retail outlets. And then we have a couple of blended products that are in the market as a soil conditioner as opposed to a fertilizer, and that's more approximate to compost. So that obviously you're going to have a heavier application rate.
Okay. The math that I'm doing as we're recording this then, at those application rates that you shared, is that this facility alone can provide the nutrient load required for like 10,000 acres of agricultural land, potentially.
Yeah, that sounds about right. So it's an enormous asset that every city in the nation produces. Not everybody produces a Class A material, but everybody, all recovery facilities produce biosolids, and if treated to the level that is acceptable by the public, it all should be returned back to the earth from which it came. It always makes me cry if a load goes to the landfill for some reason. We haven't done that for many years, but I know that some municipalities send their biosolids to landfills and trap that carbon and those nutrients in the landfill. It just makes me cry.
And what you're doing, though, is being able to take all of those resources, reclaim it, and it doesn't go to waste. It's amazing.
Well, thanks. I appreciate your interest and your enthusiasm. Often, I think we humans forget that we're part of the ecosystem. And if I could just do an analogy here, if a bear lumbers out of the woods and goes over to the river, scoops out a salmon, eats that salmon, it will use some of that salmon to fuel its body for the day or for the next couple days. But it's not 100% efficient, and it's really by design, it's not supposed to be 100% efficient. A lot of the nutrients pass through it, and it ends up on the forest floor where it is broken down by microbes, much like we do here at the wastewater treatment plant, from organic nitrogen into plant available inorganic nitrogen, and it feeds the forest floor, and it turns it into soil. And really, we should be doing the same thing. We're part of the ecosystem, and it drives me crazy when this material ends up in the landfill, because it's not the way the earth is supposed to work.
That idea that everything garden, something else's waste is nutrients or food for another.
Our mantra in my group is there's no such thing as waste, only wasted resources. And I think this is a perfect example.
So the Class A product that you're creating, you say is pathogen-free, but how are you handling pharmaceuticals and other things from human waste? Does the digestion process break those chemicals down? Is there a filtration process involved? Because that's a piece that I haven't found clear information on from the people who are doing this kind of work on a small scale.
Yeah, there's a lot that ends up in the sewers. Of course, everything that goes down our drains ends up in the sewers. And so we get very small trace amounts of a lot of these chemicals and forever chemicals. Some of them get broken down in the digester, some of them do not. We monitor for everything, even way beyond what is required by EPA. In order for us to have a biosolids reuse program certified by EPA, we have to have a pre-treatment program, which means that we have inspectors that go out and visit industries, and we issue them a permit to discharge into the sewers, and they have to adhere to certain standards of dumping into the sewers, and we go out with our inspectors and do clandestine sampling, and if we analyze the sample and we find out they're above their limits, we can cap their sewers. So they take it very seriously. If we cap the sewers of, say, a metal plater, then they're out of business. So as a result of that, and the fact that in DC we don't have a lot of heavy industry anyways, we are orders of magnitude below the limits that EPA sets for these metals and different chemicals. There are some other things that are not currently regulated by EPA, some of these forever chemicals, and we test for them anyways because we want to know where we're at. And we find that we are at background societal levels. Some of them are in Teflon pans and in plastics and in food containers and everything, and they end up in our homes, There are studies that show that some of these chemicals are in household dust at 10 times the concentration in our biosolids. It ends up in food waste because it's in the food containers. So we're way below some of the limits. Like California just set a limit for one of the chemicals in food containers, and it's 100,000 times higher than what we have in our biosolids. So we're very low levels. There are certain sites that have received industrial sludges where they've seen concentrations of these chemicals, but we make the distinction between the background levels in municipal solids and industrial contamination. We're very low, and we're very confident that our product is great for the environment.
That really opens up the door then for how we can reclaim all of these nutrients.
Some of these chemicals, they're just ubiquitous in our society. They're in our blood serum, they're in breast milk. It's not good, and it's because they are everywhere in our society. There's a study that looked at biosolids land application sites in Arizona to see how they compared to sites that didn't receive any biosolids. And the sites that didn't have biosolids had very similar levels of these PFAS. So it's just, I don't know if it's from fertilizers or pesticides or atmospheric deposition because incinerators burn plastics and it ends up in the atmosphere, but it's everywhere. So the biosolids have background levels similar to what on farms that have not received any biosolids. The real solution, if we want to get rid of it, is source control. I think that we should combine forces with the environmental community. I think that we're part of the environmental community on a campaign for source control. That's the real solution. Get these products off our shelves.
Does DC have a combined sewer stormwater overflow system, or are those separate systems?
For many years, much like lots of cities on the East Coast, it was separate. About 6 or 8 years ago, we undertook a giant project that we call the Clean Rivers Project, which is boring tunnels underneath the city, different strategic positions. They're 28 feet in diameter, and we used to have pretty routine overflow events. Every time it rained with any intensity of more than about a half an inch, we would have too much flow coming to the plant, and EPA then allows us to divert because it's better than having all that flow come through the plant and flush out all the microbes, which would take many months to regrow. So they allowed us just to do some minor disinfection and go out to the river. But that just meant that there was raw sewage going out to the river. It's awful. So now we have this Clean Rivers program and project that has these tunnels that serve as a cistern. So they capture the water, and then we wait until the rain event stops, and then we slowly feed it all through the treatment plant. It's not complete yet, but the first 2 phases are done. And the second phase of it was along the Anacostia River, and immediately when we started that up, we saw a drop in trash in the river, and it's a much more usable body of water now. It's really quite beautiful.
And which body of water are you discharging into?
We discharge into the Potomac, and that leads out to the Chesapeake Bay, which is an incredibly sensitive ecosystem. So our nitrogen limits are very low, nitrogen and phosphorus. And we achieve that through biological nutrient removal here at the treatment plant using biology, microbiology.
As you capture the water and sewage that are coming into the plant, can you walk us through the stages from where that comes into the plant through to how you get to the bloom product?
It's my favorite question. So the water comes in, raw sewage comes into the treatment plant, and it immediately goes through bar screens, which screen out giant tree limbs and bicycle tires and shopping carts and things like that. And then it goes through fine screens to screen out plastic and debris, because we don't want that, A, ending up in our pumps and gumming up our pumps, but also, B, I don't want it in my biosolids. And I can tell you there's a lot of safe sex being practiced in DC because there's a lot of evidence of that coming off the screens, and that just gets screened off and ends up in the landfill. The water then flows through to the primary settling tanks where organic matter settles out to the bottom. You can imagine what that is. It's organic matter coming in. So that's the first source of solids to go to our digesters. The water goes over the weirs of the primary tanks, and it looks clean, but it still has a lot of dissolved carbon in it. So that, and nitrogen. And that goes to secondary treatment, which is a biological process to remove the carbon, because we have a carbon limit on our discharge. So it goes through this biological process, bugs in there eat the carbon, and they get to the end, and they're all fat and happy, and they go to settling tanks. The carbon settles out. These microbes are just like water balloons filled with carbon. Settles out to the bottom, Some of them get returned back to the process to maintain the population. I guess they're the lucky ones. The unlucky ones, depending on your perspective, get sent over to the digesters. That's our second source of solids. But it's great because they are just, again, bags of carbon ready to be consumed in the digesters and to make methane out of. But the water then continues traveling on to our advanced nitrogen removal process because it still has nitrogen in it. This again is a biological process. I won't get into all the gory details, but it's super cool. We remove the nitrogen with microbes again. Those microbes go to settling tanks. Some of them get returned to the process, and the unlucky ones that go to the digesters. So now we have three sources of solids that go to the digesters. They get blended together. And this is where the fun starts to happen. We have a thermal hydrolysis process. It's the first one in North America, the largest one in the world. And it's like a big giant pressure cooker. It is a batch process, 22-minute batches at 160 degrees centigrade, not Fahrenheit, centigrade, above pasteurization. Pasteurization is 70 C for 30 minutes. This is 160 C for 22 minutes. And it's also under high-ish pressure. It's 90 psi, 90 pounds per square inch. That's about 6 times atmospheric pressure. We're sitting here at about 14 psi. So it's high pressure, high heat, and then it goes to the flash tank, which is the last tank, which is back at atmospheric pressure. So that first thing was the thermal part of thermal hydrolysis. The second part is hydrolysis because that sudden pressure difference causes the cells to burst. And now we have a sterile, very available food source. All that carbon is now available for the hungry microbes in the digesters. We have archaea in the digesters. You have archaea in your gut. It's archaea's job in nature to convert organic matter to methane. So we have the conditions perfect in the digesters for archaea. They generate methane or digester gas, which we clean up, and then we put through turbines. We have 3 5-megawatt turbines that generate clean, green, renewable energy. It's certified as a renewable energy source. We generate about 8 megawatts of power, which provides a third of all the energy we need here to run this entire plant. We're the biggest user of electricity in DC. And the turbines, when they spin, they generate a lot of heat, and you have to shed that heat or you're gonna melt your turbines. So we put heat recovery steam generators at the end of each of the turbines, pull heat off, make steam, and that's how we heat up the thermal hydrolysis process. So it's incredibly energy efficient. We don't have any external energy, outside energy sources to do that. And that is also considered to be a renewable energy source. We have certifications for those. So that's the energy part of it. The digesters aren't 100% efficient, so what does not get converted to methane comes out of the bottom as a very, very stable, low odor digestate, which then we squeeze the water out with belt filter presses, and we end up with our product that we call Fresh Bloom. That's the product that we send to farms. We have about 22, 23 trucks a day that end up leaving with product that comes out at about 31% solids, and that's our Fresh Bloom product. That then gets blended into our other products. We take some of it, we cure it, and make a soil-like product out of that as well.
And now you've got solar too.
Yeah, I could go on. We have solar. We're making a bunch of solar here, solar energy. I like my job. I don't know if you can tell.
It's still difficult for me in this moment to wrap my head around it because of how big it is.
The economics work. I'm so proud of our board for doing this, DC Water Board, because they didn't have to do this. This was a discretionary project. We could have continued lime stabilizing our material, and it was an enormous expense. It was $470 million. Normally, that amount of money is reserved for projects that are forced upon us by consent decree by EPA. We have to do it. We have to cut our nitrogen in half. And we're glad to do it, but there's no payback period on any of those. So we presented the business case to our board members, and they said, let's do it. It took some intestinal fortitude for them to do it. But that's why I like doing things like this. I always agree to do it because I like disseminating the idea that every city has this resource and every city can be doing similar projects. Economies of scale work for us, but it works on many scales.
That $460 million, on a balance sheet, I imagine that was a deficit and just part of your cost of operations.
Yep.
But now through these processes, the energy you're generating, the ability to sell this resource, that you're no longer spending that money, that it has become revenue.
Yeah, so it was a cost center for us to recycle the biosolids before, and we've had dramatic savings just from volume reduction, and then because we are selling it, we have some revenue coming in. We're selling the renewable energy credits. We're not buying fossil fuel energy off of the grid. So all these savings, the business case shows that it's got about a 16-year payback period, which is really good because the bulk of the investment is the digester vessels, and they have a 75-year lifespan. So I think it's this perfect combination of projects that make great environmental sense and fiscal sense. As part of this, my team built a carbon footprint model for DC Water because we wanted to see what it would do to our carbon footprint. We're not required to do it, we just wanted to do it, it's the right thing to do. And this one project reduced our carbon footprint by a third, by about 50,000 metric tons of CO2 equivalent emissions annually. And it's because of reduced trucking, because we have reduced volume. It is because we are sequestering the carbon back into the soil. And when the farmers use the biosolids, they are avoiding the use of ammonium nitrate, which comes from natural gas. So that is a drop in our carbon footprint right there too. So there's all these benefits. It's this rare municipal project that makes both environmental and fiscal sense, I think.
And that was Chris Peot of DC Water and April Thompson of Bloom. Learn more about the line of products from Bloom at bloomsoil.com, and more about this and other large-scale projects from DC Water at dcwater.com. Until the next time, spend each day returning nutrients to the soil while taking care of Earth, yourself, and each other.